All right, so I'm doing a recording of this class. I'll post a link to the video after class. Did have somebody request it, and I remembered. All right, so what we're looking at, this is updated module 10, the sum to product, product to sum formulas, which we're really only doing product to sum. And then we're going to start looking at trig equations. So these particular formulas here are, we don't even put these on the test. We only cover these formulas because they show up in a electrical engineering course. Yeah. Like honestly, I never even saw these in math until I started teaching pre-cal here. So that is how rarely these particular formulas show up. And it's because they're like it's cosine alpha, cosine beta. So we have two different angles. And most of our math work, we only have one variable. We don't actually start looking at multivariable anything until Cal 3. So these formulas might show up in Cal 3 if you actually have the very particular instance of having trig of one variable times trig of another variable, then this would be useful in Cal 3. So that's why it shows up in electrical engineering. Electricity is modeled by sine and cosine waves. So there's a particular instance where this is useful. But even then, they're like, all right, so here's this formula you probably don't remember. Here's how we use it. All right, good. So, ooh, that's broken. So that's how we're going to treat it. So our question here is find sine of 6 theta times sine of 4 theta. Make this big screen. So we're going to write down the formula for sine A, sine B, or sine alpha, sine beta, whatever. So all of our formulas start with this 1/2 in front. And then this is cosine A minus B minus cosine A plus B. So sine of 6 theta, we can call 6 theta A. So everywhere there's an A, I'm going to write 6 theta. And then everywhere there's a B, I'm going to write 4 theta. But everything else in the formula I'll keep exactly the same. So 1/2 bracket cosine 6 theta minus 4 theta minus cosine of 6 theta plus 4 theta. And then all we're having to do from there is just do the subtraction or addition inside. So 6 theta minus 4 theta is 2 theta. And then 6 theta plus 4 theta is 10 theta. And then we're just pattern matching, which is, for me, the fourth answer. So this is very much just making sure you're picking the right formula, being careful about your substitution, clean it up a tiny bit. There's your answer. So what questions do y'all have on this one, the way it shook out? All right, let's see the next one. All right, so now our setup is a little weirder. They put fractions for no good reason. And they have an 8 in front. All right, so we're looking at cosine, cosine. So that's our top formula. So we've got the 1/2 cosine A minus B plus cosine A plus B. All right, so our formula is just for cosine ugly, cosine weird. Our question, though, also has this 8 in front. So we're going to copy the 8 down in front. And then we're going to trade out our cosine AB for the formula. And the formula starts with a 1/2. So I have 8 times 1/2 on the outside. And now I'm going to work the inside. So we'll have -3/5 x minus -3/4 x, the cosine of that, plus the cosine of -3/5 x plus -3/4 x, which is just very much a y. Why did we have such a ridiculous looking thing? All right, so 8 times 1/2 gives us a 4. And this is absolutely the point where I would pull out a calculator because to hell with doing all that bullshit by hand. So we need to know what -3/5 minus -3/4 is. That is apparently positive 3/20. So we have the cosine of 3/20 x plus the cosine of, now we have -3/5 plus -3/4. And that is -27/20 x. Ugh. And then here, the question is being a little stupid. So cosine is an even function. It's symmetric across the y-axis. It starts at 1, goes down and comes back up, and then to the left, it goes down and comes back up. So it's the same pattern folded on the y-axis. What that means is the cosine of negative x is the same as the cosine of positive x. So my cosine of negative 27/20 is the same as the cosine of positive 27/20. Now, if I had like +2 or -3 in there, if I had addition or subtraction, I couldn't make this change. But once I've combined the like terms, now I can absorb the negative. So that's why my fourth answer choice is what I picked. But usually the green answer we got, that's where I'd stop. That's what I'd type in for this. Because I don't think the web work is multiple choice. The amplify happens to be. Now, it's not incorrect to make that change. It is equivalent. It's just not necessary. So what questions do y'all have on how we moved through this one? So cosine of, here, let me doodle on the screen. So because cosine is an even function, if I have a negative times x, even if there's a number there, as long as it's just multiplication, I can strip away the negative. Like it's a known identity that cosine of negative x is the same as cosine of x. Most of the time we don't bother using this identity, but that's why we had the negative and then it like disappeared. And that was just to like show you why the answer we got in our list is equivalent. But the answer that I wrote in green, the line before that, is also perfectly fine. That's also the answer. It just wasn't in the list. All right, so our next one, now I've got a sine cosine. So there are technically two formulas here. There's a sine alpha cosine beta, and there's a cosine alpha sine beta. Those two formulas are equivalent. It requires a little manipulation, but it doesn't matter which of these two formulas we use, as long as we're making sure that whatever is inside the sine is where we put the alphas, whatever is inside the cosine is where we put the betas. Like alpha minus beta is not the same as beta minus alpha. They are slightly different. Depending on the trig function, though, they may be equivalent. So since they wrote sine first, I'm going to go with the sine first formula, but you could technically use the last one as well. So sine A cosine B equals the annoying 1/2 times sine A plus B plus sine A minus B. So this equals 1/2 sine 3 pi over 8 plus 15 pi over 8. Then the formula has plus in between. Sine 3 pi over 8 minus 15 pi over 8. So 3 plus 15 is 18 pi over 8, which will reduce, but we'll do that in a second. 3 minus 15 is negative 12 pi over 8. All right, so 18 and 8, we can change that out for 9 pi over 4. Plus, we distribute the 1/2 sine of yeah, 3 pi over 2, but our added identity here is the sine of negative x is negative sine of x. Sine is an odd function, so the negative actually, as long as it's just negative of a number, not negative number plus or minus something, then that negative can come out. So we can actually write this as a minus in between and leave it as positive 3 pi over 2 then. And that gives us our ridiculous second answer here. Now you shouldn't have to make these trade-outs on web work, but I think there is like one kind of which of these are equivalent question, and they might make these trades for the equivalent parts. But it's always sine and cosine, so you only have to know the rule for sine and cosine. And I think of it as cosine of negative x is saying left side, cosine of positive x is saying right side. If the graph folds on the y-axis, then the left side equals the right side. For the sine graph, it doesn't fold on the y-axis. It's a 180-degree spin to get the same graph. So that's why we have the negative inside versus the negative outside. All right, we got one more of these. So now this one is a little extra silly, but the formula will still work. So we have sine of 17 pi over 12, cosine of 17 pi over 12. Wait, yes, I said the same angle twice. So we can do it this way, but there are actually some other ways to handle this problem, and it means our answer is going to look a little weird. All right. So sine A, cosine B. We got our 1/2 sine 17 pi over 12 plus 17 pi over 12. Then plus the sine of 17 pi over 12 minus 17 pi over 12. So over here, the thing minus itself is 0, and the sine of 0 is 0. So this second part actually completely goes away. So we're just left with 1/2 the sine of 17 pi over 12 plus 17 pi over 12 would be 2 times 17 pi over 12. And then the 2 and the 12 reduce, so it's 17 pi over 6, which is our first answer. So questions on the product sum formulas. All right, then what we're going to look at next is now solving trig equations. So solving a linear or quadratic equation feels pretty normal, but now we're going to put a trig function in there and everybody loses their mind. So since trig functions are periodic, they have infinitely many solutions. When we're solving sine and cosine trig equations, their period is 2 pi. So all the solutions, when we find a theta that works, that theta plus 2 pi k, where k is any integer, is going to be the full list of solutions. So that k thing that we kind of hinted at before but kind of ignored, now we're going to make use of it. So let's just consider a very basic equation. Cosine theta equals 1/2. So where on the unit circle is the cosine 1/2? Yep. So down at 5 pi over 3, my cosine's positive. That's quadrant 4, and up in quadrant 1. So pi over 3 and 5 pi over 3. So those are the particular solutions between 0 and 2 pi. And then all the solutions, and I have no way to stop the animation, are pi over 3 plus 2 pi k and 5 pi over 3 plus 2 pi k. So we find the numbers off the unit circle, and then we write plus 2 pi k. So anytime we do that translation from the unit circle to writing down a number, we're going to put plus 2 pi k with it. All right, let's look at the next one. So now, a lot weirder. Now we have the cotangent of theta plus 1 over the square root of 3 equals 0. So we're going to have to think a little more about this one. But cotangent of theta, I can minus that 1 over the square root of 3 to the other side. But now I want to think about what cotangent is. So cotangent is 1 over tangent. Tangent is sine over cosine. So cotangent is the flip of tangent. So cotangent is cosine theta over sine theta. And we're asking, when does that ratio equal negative 1 over the square root of 3? So the original setup here, it looks like it's saying, where is cosine negative 1? Where is sine square root of 3? Sort of. Remember, whenever we divide a cosine over a sine or a sine over a cosine, and we're pulling those values off the unit circle, the over 2 that shows up in all those answers cancels out. So I'm going to put the over 2 back into this weird fraction here. So now we can see this is saying, when is the cosine negative 1/2 and the sine is square root of 3 over 2. Or I could move the negative, so I could have a cosine of positive 1/2 and a sine of negative square root of 3 over 2. So if I have either of those setups, when those two cosines and sines divide, I'll get negative 1 over the square root of 3. So now I want to find these locations on the unit circle. So when is the cosine negative 1/2 and the sine is positive square root of 3 over 2? Yep. So our first answer is 2 pi over 3. Now what about our flip side? Cosine's positive down in quadrant 4. Sine is negative in quadrant 4. And generally when you've got one of the over denominators, it's going to be the same denominator. So 5 pi over 3, there's our other one. So those are our two particular solutions. But then I'm going to tack on plus 2 pi k. And those are what we call the general solutions. So the particular solutions are just the solutions on the unit circle chart. The general solutions are the k formulas that would give me the full infinite list of answers to the equation. So if I plug in 2 pi over 3 and I figure out the cotangent of that, I'm going to get negative 1 over the square root of 3. And then I add that to positive 1 over the square root of 3, and it equals 0. If I plug in 5 pi over 3, same thing will happen. If I plug in an angle that's coterminal, I'll also get the same result. So when we make this initial change, yes, it will be 2 pi k. We're going to see more complicated equations later where we're going to have to make some modifications to the 2 pi k. But that'll be because it won't be cotangent of theta, it'll be cotangent of extra crap with theta. So for this step, when I'm going from trig function of stuff and I'm writing this stuff equals an angle from the unit circle, it's always that angle from the unit circle plus 2 pi k. So I know that was a long answer to where it's like it should have been a yes or a no, and the answer in math is sort of. So we'll see as we move through them. Yes, so 2 pi over 3 and 5 pi over 3. Now, 2 pi over 3 and 5 pi over 3, if you look on the unit circle, those two angles are actually collinear. They are pi radians apart. So instead of writing the 2 pi k on each of them, we can actually write it as a singular formula, but this is only the case because we're looking at a tangent cotangent function. Most of the time, the formulas cannot be combined. So I'd rather we focus on the two separate formulas because that also produces the infinite list of answers. So what other questions do you guys have on how this one played out?
Can you forget why it took it and divided it by 2 and the purple step?
Yeah. So I changed cotangent for cosine over sine. So now I was looking at two different numbers equal to two different trig functions. So when I look at cosine theta equals -1 on top and sine theta equals square root of 3 on the bottom, like I can find a spot where cosine is -1, but there isn't actually a spot where sine is just the square root of 3. Square root of 3 is actually too big. But when I look at my trig functions up here, basically what I'm doing is I'm multiplying the top and the bottom by 1/2. And I'm doing that so that these numbers look like stuff on the unit circle. Because if we were actually calculating like the cotangent of 2 pi over 3, I'd go look up at 2 pi over 3, cosine is -1/2, divided by sine is square root of 3 over 2. And then the half parts, the over 2's would cancel. So I was just like undoing, canceling the over 2's. So it looks weird when we're going from this direction. But like when I do it from putting in the angle, then my over 2's get canceled. So that's why I put them back in, just so we could actually line it up with, then I'm really looking at where is the cosine -1/2 and where is the sine positive square root of 3 over 2. We only have to do that because we're looking at a cotangent or a tangent function here. Most of the time, it's just going to be sine or cosine equals number. All right, let's see what the next one brings us. All right, so now we've got to do a little algebra manipulation. So 2 sine theta plus the square root of 3 equals 0. So our goal is to try to get theta by itself. Well, theta is attached to sine, so I'm going to get sine theta by itself. So there's a 2 being multiplied and a square root of 3 being added. So I'm going to deal with my addition first, minus the square root of 3 from both sides of the equation. So I have 2 sine theta equals negative square root of 3. Then I divide by 2. And now I'm looking at something that's actually on the unit circle. Where is sine theta? Negative square root of 3 over 2. Yep, so 4 pi over 3. And where else? Yep, 5 pi over 3. So we can, if we think about our all students take calculus, sine's positive in quadrant 1 and quadrant 2. We're looking for a negative, so we can like shortcut our, just look in quadrant 3 and 4. And it's also, once we find one of them, just go look at the multiples with that denominator. So 4 pi over 3, check 5 pi over 3. 2 pi over 3 was positive, pi over 3 was positive. So yeah, 4 pi over 3 and 5 pi over 3. Now we pulled angles from the unit circle. So we write the plus 2 pi k. But this question had the added caveat for theta between 0 and 2 pi. So we only actually have to answer the 4 pi over 3, comma, 5 pi over 3. Read that. So this is the general solution. And just the 4 pi over 3 and 5 pi over 3 are the particular solutions in our 0 to 2 pi range. And let's see what our next one does. So now it's getting a little ugly. So we have 2 sine squared theta minus 1 equals 0. So still we can start it out the same way. I'd add the 1 over, so I'm going to skip writing that step. And then divide by the 2. So we have sine squared theta equals 1/2. Now, what do I do to get rid of the squared? Yep. Now, what do we have to remember with square roots? Yep. So we technically have 2 different equations now, 2 different solutions. Sine of theta could be the positive square root of 1/2. Now, before I write that though, because square root of 1/2 is not on the unit circle, so we're going to make a little adjustment. So this is really the square root of 2 over square root of 2 times square root of 2 on the bottom would be square root of 4, which is 2. So this is sine theta equals positive square root of 2 over 2 and sine theta equals negative square root of 2 over 2. Now, each of these trig functions has two answers. So when I have trig function equals number, typically I'm going to get two answers from that. Sometimes I will get just one answer if it's trig function equals positive 1 or negative 1. And sometimes I can get a really silly equation like sine theta equals 7. Sine theta never gets as big as 7. It's always between 1 and negative 1. So in that case, we would have no solutions. But the most we'll get, and typically we get two solutions from each of these trig equations. So what two angles have a sine of square root of 2 over 2? Yep. But because up here they say theta is between 0 and 2 pi, we're going to go with the radian measures. But if you want to write degrees on your paper and then just trade it out for the radians, that's fine as well. So pi over 4 and 3 pi over 4. And then when is sine theta negative square root of 2 over 2? That's going to be our other 2 over 4s, 5 pi over 4 and 7 pi over 4. So because this was a quadratic trig equation, we actually ended up with 4 solutions. Technically, it's 4 infinite lists of solutions, but between 0 and 2 pi, it's just 4 particular numbers. So pi over 4, arrow over comma, 3 pi over 4, arrow over comma, and then 5 pi over 4, and 7 pi over 4. There's our great job. Now, if you think back to college algebra and how many different equations, kinds of equations you had to solve, all the different strategies for solving those equations, like there's a lot of equation solving skills we have. And now we're saying, all right, trade out those variables for trig functions, but now go back and solve all those kind of equations. So there's a lot of examples here. If you looked at the videos on solving trig equations, or when you look at those, there is 7 different videos. Each of the videos, though, is pretty short, but that's because there's so many different ways we could solve equations. So when you look at the notes, the guided notes, I basically do about 2 examples per video. So if you want to go look for a particular example, just kind of like, all right, first and second, that'll be in the first video. These 2 will be in the next. So just like every other one to kind of guesstimate which video it'll be. All right, now this one does something silly. They say, put theta between 0 and 4 pi. Okay, sure. But they're giving us the weird little equation cosecant of theta equals negative 2. Well, my unit circle doesn't have cosecant, but I do know that cosecant is 1 over sine. So I'm going to trade that out. So if 1 over sine theta equals -2, like -2 over 1, I can reciprocal both sides. So I have sine theta equals -1/2. So where is the sine -1/2? So it's not quadrants 1 and 2. Yep. And then the other over 6 is 7 pi over 6. All right, so this is where we put the 2 pi k. So this problem, because they expanded our range of answers up to 4 pi, we're actually going to make use of the 2 pi k part. So 7 pi over 6 and 11 pi over 6 are the first two numbers in my answer. But those numbers are coming from the part of the list where the k value is 0. So k here can be any integer. So 0 is our most basic right in the middle integer. And if I plug in 0 for k, I'm going to get 7 pi over 6 plus 0. So we just get 7 pi over 6. And we get 11 pi over 6. Now, to get the other two solutions that are from 2 pi to 4 pi, I need to find the coterminal angles with these two. And that's all the 2 pi k is a placeholder for. It's just saying these two are the starting numbers in the list, and then 2 pi k gives us all the coterminal angles, all the ones after it and all the ones before. So if I do 7 pi over 6 plus 2 pi times 1, 7 pi over 6 plus, that'd be 12 pi over 6 is 19 pi over 6. And then 11 plus 12 will be 23 pi over 6. So we have 4 answers. Ah, forgot to hit the comma. So we plugged in 0 for k just to show that the two numbers we got from the unit circle are actually the first two solutions. And then I picked 1 because our bounds on theta were from 0 to 4 pi. So 0 to 2 pi gives us the two numbers we get from the unit circle. Expanding it up to 4 pi means add a 2 pi, get the next larger coterminal angle. So that comes from k equals 1. So k being any integer is really just a way of saying any of the coterminal equivalent angles. Then just picking the k values is just the algebraic way of symbolizing I'm picking those coterminal angles. Like if they said from negative 2 pi to 2 pi for our range, I would have picked k equals -1 because that would have given me the less than coterminal angles, the negative coterminal angles. We usually don't need the negative angles, but it's not impossible. Like especially if depending on how you set up a machine, like sometimes you make 0 like your starting position and then you just increase the angle. But sometimes 0 is actually your middle position and you've got increase the angle and decrease the angle. So sometimes you actually need to be able to include those negative numbers, but it really just depends on the context of the problem for what you'd set it for. And then we get something stupid like this. And I say stupid because now the unit circle will not help us. The numbers we're going to get are not going to be on the unit circle. So we're actually going to have to use some thinking and trig formulas and reference angles here. But our initial start, cosine squared plus 3 cosines minus 1. That looks horrible in terms of cosine. So our first thing is we're going to make a creative substitution. And I use U for my substitution because U stands for ugly. And what's making this ugly is the cosine. So if I say ugly is cosine theta, then my equation here where it's cosine squared, well, that's now ugly squared. Plus 3 cosine is 3 uglies. Minus 1 equals 0. So now I'm looking at a quadratic. But what makes this quadratic annoying is this quadratic does not factor. So I have to use the quadratic formula here. So that's why our answer choices are all decimals. When we're using the quadratic formula, we're going to get really ugly looking numbers, and then we're going to have to use an inverse trig function and get even more ugly looking numbers. But let's start with our quadratic formula. So normally the quadratic formula starts with x equals because the standard form quadratic is written in terms of x. Our quadratic is written in terms of u, so I'm going to write u equals for the start of our quadratic formula. So u equals negative b is a -3 plus or minus the square root of 3 squared minus 4ac all over 2a. I didn't even learn it to Pop Goes the Weasel until I was teaching, but now anytime I do it, that's what comes out. All right, so the quadratic here is going to give us two different answers, one from the plus root, one from the minus root. But let's just clean it up a bit. So -3 plus or minus, so 3 squared is 9, and then it'll be -4 times -1 will become +4. So we're going to have the square root of 13 over 2. All right. Now we just did a whole lot of work. We're only halfway done. So now I need to know what those decimals are. So -3 plus square root of 13 all over 2. And my calculator was being a smartass, and it was like, here it is. It's what you typed in. No, I want the decimal. And then we get negative 3.30277. All right, but that's just what U equals. Now I'm going to use my substitution again. So U is cosine theta. So I have cosine theta equals 0.30277. And I have cosine theta equals negative 3.30277. I need to know what theta is. Now, this is normally the point. If we got like numbers we see on the unit circle, like if we had a half coming out of the quadratic formula, I'd go look at my unit circle. But 0.3 is not one of those numbers. So what we're going to have to use to figure this out is the inverse trig function. So we're going to apply inverse cosine to both sides of this equation. Now, because they told me theta is between 0 and 2 pi, I have to be in radians mode. So I flipped it over to radians mode. And now I'm going to do second inverse cosine of 0.30277. 0277. So this gives me 1.2631 blah, blah, blah. Now, when I try to do the same thing over here, can I have a cosine of -3? Can I have a cosine that big? Like, think about the graph of cosine. What's the highest cosine gets? 1. And the lowest is -1. So do we ever get all the way down to -3? Not unless we have an amplitude, but there's no amplitude in front of this. So this -3 is impossible. If I type this on the calculator, I'm going to get an error. So this part gives us no real solution to work with. So we just chuck that side out as, okay, you're useless. But this 1.26 we got here, this actually does have another answer hidden inside of it. So remember, our inverse trig functions are range restricted. They can only spit out certain numbers. So I have to think about where this angle is and where the other angle that would have the same cosine would be on the unit circle. So 1.26, like the cosine was positive. So this is somewhere in quadrant 1. And the cosine is that 0.3, blah, blah, blah. So where else is going to have that same cosine? Like in what quadrant is this other angle going to be?
4.
Yep, quadrant 4. That's the other quadrant where cosine is still positive. So that's going to be down here. Now, when I'm looking at my angles, The theta equals 1.26. That's our reference angle. This is going to be the same 1.26. But I want to know, how do I get that angle measure for this guy here? So I look at, this is a whole entire circle and then minus 1.26. So I'm going to calculate 2 pi minus the 1.2631. So 2 pi minus my previous answer. This gives me a secondary weird answer of 5.0199, blah, blah, blah. So we get the 1.26, but we also get the 5.02. Now this is like the craziest, or one of the ways it can get crazy. It could have been a little crazier because the negative 3.03 could have been an actual number, and then we would have had 2 more answers over there. But in the real world, this is like more likely what would happen. And depending on the context, you might actually say like 1.26 and negative 1.26. Like those might be the 2 answers that actually make the most sense in the context you're going with. Or you might convert them to degrees, or really you convert them to gear rotations usually. Now, this is a little too ugly for the test, having to work with the getting a weird decimal number and then having to configure through what the other decimal number would be. But there are just a few on the web work that will do this. On the test, though, we keep it on the unit circle. And on the test, we tend to keep it factorable, so you don't have to use the quadratic formula. Now, technically, this is 1.26 plus 2 pi k and 5.0199 plus 2 pi k for the general solution, but they did only limit us to the 0 to 2 pi, so that's why we cut it there. All right, let's see what the next one is. A 3 theta. All right, well, let's start thinking about 3 theta. So before we really deal with that 3 theta on the inside, like just think of it as an ugly. So I have 2 sine ugly equals square root of 2. So what's the first thing I'm going to do to start getting at the variable? So if I'm just thinking of this as a regular equation, the way I look at equations is I zoom in on the variable and then I start looking at what's with the variable. So there's a 3 being multiplied to the variable. So at some point, I'm going to want to divide by 3 to get rid of that 3. Then outside that, there's a sign. All right, I'm going to have to do some trig nonsense to get rid of the sign. And then outside of that, there's a 2 being multiplied. So how do I get rid of this 2 on the very outside? Yep. So that's going to be our first step. So we focus in on theta. look at all the operations close to it until we get to the very outermost operation. Now, it's kind of weird to deconstruct an equation that way, but if you can focus on the operations like that, that really helps you see the function composition, which is what this actually is. This is functions composed together. So our first step, we're just going to divide the two. So I now have sine of the weird 3 theta equals square root of 2 over 2. Math. All right, so now, again, just ignore the 3 theta. That's just what's inside. When is the sine square root of 2 over 2? Yep, pi over 4 is one of them. So I've got 3 theta equals pi over 4. And we think about our all students take calculus, sine's positive in quadrant 2. So our quadrant 2 over 4 angle is 3 pi over 4. So right here, I did my unit circle, look up the trig function, trig thing step. So this is the step when I write the 2 pi k. But now notice what was inside the trig function wasn't just a theta, it was a little weirder. Now I have to deal with that weirdness. So that 3 inside, how do I get rid of the 3? Like, how is the 3 attached to the theta? Yep, 3 is being multiplied, so we're going to divide by 3 to get rid of it. So when I divide both sides of the equation, I divide both entire sides by the equation, by the 3. Or I can write that as multiplying by 1/3. But that divide the whole thing or multiply by the fraction, that's going to apply to both parts. So we now have our theta by itself finally. We have the very weird pi over 4 times 1/3 is pi over 12. And now our 2 pi k becomes 2 pi over 3k. 2 pi over 3 times k. And then 3 pi over 4 times 1/3. The 3 on top cancels that third, so we have pi over 4 plus, but again, it'll be 2 pi over 3 times k. So that's our general solution. So a little weird, but that's not too bad to stop at. The problem is, though, they actually said, what are the solutions in the interval from 0 to 2 pi? So that 3 theta means we have 3 times as many solutions. So I have 2 solutions right now. 2 times 3, I'm going to get 6 numbers on my list. So this is where the k values come into play. So we're going to have to use 3 k values to get the full complete list. So we're going to use, starting is k equals 0, because that gives us our first basic angles from the unit circle. But then, because it's 3 theta, I'm going to use 2 more k values, and I just use the next 2. K equals 1, and k equals 2. So now it's a whole lot of tedium. So when k equals 0, I'm going to get pi over 12 plus 2 pi over 3 times 0, which is just going to be pi over 12. Our next one, now we actually got some fraction math. So pi over 12 plus 2 pi over 3 times 1. On your calculator, if you can't type it in with the pi's, type it without the pi's. 1 over 12 plus 2 over 3. And mine spits out 3/4. So this is 3 pi over 4. And then I have pi over 12 plus 2 pi over 3 times 2. And this tells me 17 over 12. So I just sneak the pi back in, 17 pi over 12. All right, now we're going to go back and do the same thing for the other equation. So pi over 4 plus 0 is just pi over 4. Pi over 4 plus 2 pi over 3. So 1/4 plus 2/3 is 11/12. So 11 pi over 12. And then last one, pi over 4 plus 2 pi over 3 times 2. Go back in, put a times 2 on the 2/3, and I get 19 pi over 12. So we got 6 answers. Now we don't do 3 theta on the test, but we might do a 2 theta. We haven't written the next test, so we got to argue about it. Me and my colleagues, but so it takes a little bit of getting used to the K values, but like once you get it, it's like, oh, it's just the same thing over and over again. I just got to punch stuff on the calculator. But it is a little bit to wrap your head around it first. All right, so we'll keep looking at the trig equations next Tuesday.